Are you single? You're single? I mean, I have a table.
Yeah, I think the lights up here are all off.
It's hard to say. Because I called them Let's start. So, some of you have emailed me about questions about homework 1. So, if you have any serious concerns, you can come talk to me after class today. But yeah, in general, this is the assignment of the TS, and this is who you should be asking for questions. So the other thing is, so last time I said that I'll try to schedule the final on Tuesday, but unfortunately there's apparently something else happening here on Tuesday. So we have to stick with the official schedules, as you were saying, so I don't think we can modify that very easily. So the official schedule is the Friday the 16th. Okay. So if it's, if any of you cannot make it, write me an email, we can see if there is some alternative we can work out. But in general, tentatively the exam will be on Friday the 16th, and it will be 10:30 to 12:30. So any questions about this? Okay, and as some of you probably noticed, homework 3 is out. Okay, so it's about NP completeness and so forth. So, and a little bit about graphs. So I noticed that there are some questions where some of you might not have background. Okay, so please go through the questions early, and if you have any definitional questions, make sure you post it on this board, okay, on this discussion board. So it looks long, but it's actually not very long. Okay, so you should, if you're having trouble, it could be a definitional thing. So ask the TAs or ask people. All right. So great. Okay. So we've been looking at graphs, and last week we saw a bunch of things for shortest paths in graphs. Right. So we saw the famous Dijkstra's algorithm, and we basically said that if you have directed graphs with non-negative weights, then Dijkstra's algorithm works very well. We also said that for non-negative weights, directed and undirected are roughly the same. So this is something we saw last time. Then we said, okay, so if you have negative weights, then undirected graphs have issues, because you have, by default, you have some cycles if you try to replace an undirected with two directed edges. But there are ways to get around it. Okay? So, and then we also saw this Bellman-Ford algorithm, where if you have a directed graph with no negative cycles, okay, so there could be negative edges but no negative cycles, then this algorithm, we saw how to find the shortest paths. And we also saw this all-pair shortest path problem, which is just a generalization of this. So we saw single source shortest path, and then we also saw what's called all-pair shortest And last class we also started talking about the spanning tree problem. Okay, so this is this interesting question where you have an undirected graph, and what you're interested in is you have a weighted undirected graph. What you're interested in is finding some kind of a minimal communication backbone. Okay, so you want to pick a subset of the edges so that everyone is connected to everybody else, and the sum of the total weight of the edges you pick is minimized. Okay, so this is the spanning tree problem, minimum spanning tree. And so the problem is you have a weighted undirected graph and you want to find a subset of edges so that everyone is connected and the total weight is minimized. And the main idea in Kruskal's algorithm was that was this very simple observation that if you take any edge that has the minimum weight among all the edges in the graph, okay, so an example could be like in this graph 2 is the minimum weight. Right? We said that there exists a spanning tree that contains this. It's a simple claim, and then we also said that okay, there could be more than one of these minimum edges. It only means, this claim only means that for every such edge there is a spanning tree containing this edge. Okay, so it does not mean if there are multiple edges there is a tree that contains all those edges. Okay, so this is something to bear in mind. And we saw that implementing this in time that is roughly m plus n is actually tricky. And we hand waved one way of doing this. Okay, so we said that you keep track of these groups of nodes, and we said, so it turns out you can implement this in time m plus n times log n. There's an extra log n. And if you're very clever, you can get m plus n log n. Okay, so we won't get into that. Okay, so last time I started off by defining this algorithm. Okay, so I said, so let's consider a more natural greedy algorithm where the idea was very simple. So you start with any vertex in the graph. So let's say I start with this guy, move to this. So conceptually think of like merge. So, and this way, so is the algorithm clear? Okay. So why would you span the full graph? If the original graph is connected, this will also be connected. Okay. And why is that? I mean, I guess it's clear, but just to convince yourselves.
Because we are considering all the edges corresponding to.
Yeah, so you have a component at every step. You have some connected component, and you're looking at all possible edges outside this, going outside. Okay, so you have to go outside. You can never get stuck. It's basically very easy to see. Okay, so this is a simple algorithm. This is also pretty easy to implement in time m plus n log n. And so we saw why this is true last time, right? So basically what we said was, all you have to do is keep track of all the edges that are going out of your connected component at this time step. Okay? So initially you just have one vertex, and the set of edges you're considering are all these things going out of this. Then you add one more vertex into this, and you have to add the rest of the edges that are connected to this guy, right? So you have to add the edges connected to that vertex. Then you delete edges that are between these. So it's but you can easily see that every time you add or delete edges, it's you are only adding or deleting. So suppose at this iteration I am adding this vertex. I'm only adding or deleting edges from your candidate set that are incident to this. Okay, so in this case the 7 or the 8 will be deleted. Okay. Okay, so the amount of processing you do is related to the vertex I'm adding. And last time we saw some data structures, so you can easily convince yourself that you can have addition and deletion. I won't go into the details, but this is actually very easy. Okay, so you can do this in time m plus n times log n, because again you have every time you add a vertex, you do work proportional to its degree times log n, and that's it. The sum of the degrees is n plus n. Okay, so this is fast. This is easy to implement. Okay. Now, why is this correct? Right. So this is a tricky thing. So in this case, the argument turns out to be a little bit more tricky than the algorithm for Kruskal. And okay. So this is also I wanted to illustrate this because this is a little bit different from the kind of argument we've been seeing. Okay, so I mean the first thing is okay, so construct, and remember this was done by, let's say, starting with this vertex and then you took the smallest edge neighbor and so on. Okay. So the vertex, the tree we constructed has some kind of ordering, right? So it has some 1, 2, maybe 3, 4, something of this kind. So this is the set of vertices that we considered, and this is the order in which we consider. So we start off by trying to argue the same, the usual way we do, which is we say that consider a minimum spanning tree. Okay, so suppose this is not the thing we considered is not the minimum spanning tree. We'll say that okay, consider that as much agreement with the tree we constructed as possible. Okay, agreement means in terms of the number of edges that overlap. So agreement is okay. So is the definition of this T clear? Some T, which is a minimum spanning tree. Okay, so this is one of the optimum solutions. There could be many optimum solutions, remember, to minimum spanning tree, right? So we are considering the one that has the most agreement with the tree that we considered. And we'll say, essentially this argument will say that if this T is different from our tree, then you can actually come up with a minimum spanning tree that agrees more with our tree. Okay. And that means that that means you got a contradiction, right? So you could not have had a different T different from our tree in the first place. Okay, so is this reasoning clear? So it's kind of a clever argument. Okay, so what we're saying is consider the tree that agrees the most, the minimum spanning tree that agrees the most, and if T is not equal to our tree, we'll end up producing a new tree, okay, a T prime, that is also a minimum spanning tree, and it agrees and it has a greater agreement with our tree. Okay, and that means that, you know, so that's what we're going to show. So the goal is not equal to our tree, then there exists a T prime that has greater agreement with our tree, and T prime is a minimum spanning tree. Okay. So, and in particular what this means is cost of T prime is less than or equal to cost of T. So this essentially says that so you must have T equal to our tree. Okay, so otherwise you have a contradiction. So how would you prove this? So I guess the hint is here. So you're saying consider the first disagreement, right? So first in this order in which we build the tree. Okay. So So you have this our vertex 1, and let's look at so let's say this is the edge we added first, and then this is the edge we added next, and so on, right? This is the order in which we added the edges. And I'm saying look at the first disagreement. So it could be that let's say you consider the first edge. Even suppose this first edge was not in the actual tree. So what does this mean? So T is the minimum spanning tree, right? So suppose the first edge in T. So T was also a spanning tree, right? So T connected every vertex. So every vertex to some every other vertex. So in T itself, so this is T I'm drawing. So there had to be a path from 1 and 2. Okay. So if you isolate this vertex 1 from the rest of the graph, then we are saying that in T there is actually a path from this, which means that out of 1 you must have chosen some edge that goes out of 1, right? And choosing. Okay. This is in T. But our algorithm was actually picking the minimum edge out of 1. Right? That was the definition of our algorithm. We were picking the minimum edge out of 1. So we know that this thing has weight smaller than or equal to this thing has a weight smaller than or equal to this. So if I swap this edge with this edge, so you get a tree, and its cost is not more than the cost of T, right? Because you swap one edge which is of bigger weight with an edge of smaller weight. Okay. So if this edge weight was 2 or 1, let's say, and both could have been 2 also. Okay. So you get this new tree which we call T prime. And this T prime, it has cost, it satisfies this property, and it's also a spanning tree. So why is it a spanning tree? Everything that was okay, and you replace one edge with this other edge. Okay, so and this you can easily check. This maintains connectivity. So any questions about why this is connected? So hopefully all of you see why this is connected. So, and this is what we needed, right? So we said that you will come up with a T prime that has a greater agreement. Okay? Because earlier so was not present in T, and now we are saying that it is present. Okay, so now we replaced it with an edge that is present. So this has a greater agreement. Okay, so is this argument clear? So yeah. Actually, there's a subtle point here which I'm hoping somebody will notice. So I was just waiting for that. So the way I wrote it, it's not guaranteed that this guy is not in the original tree, right? So that this edge is not in the original tree. Could also have been. Okay, so. Well, I'll let you guys think about this. Okay, so this is not strictly making an improvement. This is making an improvement in the sense that now you have the first edge in this new tree. Okay, so you'll have to phrase this argument a little bit more differently, but yeah, hopefully you'll be able to figure this out. So is this slight issue clear? Okay. So yeah. Okay. All right. But you can see how this argument can be finished, right? So you will say that there is a T prime which is also a minimum spanning tree and contains our first edge. Okay. and then you'll say there is a T prime that contains our first two edges, okay, and then there's, and so on. So that's how the argument basically flows. So, alright. Okay, so this shows that basically there exists T prime that is an MSE and contains our first k edges for every k. Okay, so you could think of this as being roughly the argument. Okay, so what I showed here is for the case k, and once you show it for higher k. Okay, so this is Prim's algorithm, and we've seen that it's correct, and it's much simpler than Kruskal's algorithm in some sense. Okay. But the running time of this is O of m plus n times log. Okay. So is the algorithm clear? You start with a vertex and then greedily grow your component by adding the least weight edge out of your component. Okay, so before we move on, a couple of comments about spanning trees. Okay, so firstly, note that when we considered minimum spanning tree, we moved to undirected weighted graphs, weighted undirected graphs, but we never really considered directed graphs. Okay, so anybody see why? I mean, you could have defined the same problem, right? You could say that I want a minimum weight subset of edges such that every u, for every uv, there exists a path from u to v. So this problem actually has a name. It's called the minimum weight strongly connected subgraph. Okay, because in directed graphs, this is what was the definition of strong connectedness. Right? So for every u, there's a path from u to v and v to u. Okay? So this is called min weight strongly connected subgraph. But it turns out this is actually NP hard. Okay, so that's why there's no. So the natural directed version of minimum spanning tree is actually NP hard. It looked at Hamiltonian cycles, but if we had, then this would actually be an almost immediate reduction. Okay, so so even on unweighted graphs, this problem is difficult. Okay, because Hamiltonian cycle means there is that the answer to this is n essentially. Okay, so if you guys know it, think about this. Okay, so this is a direct reduction from this problem called Hamiltonian cycle. Okay. So this is the reason we only considered undirected graphs when it came to spanning trees. Okay, so the directed analogs are hard. Okay. And note that all the algorithms we mentioned have time roughly O of m plus n times log n, and log n. In this, this is the Kruskal's algorithm. So there's been a lot of research. So you might wonder why people care so much. Actually, I also don't know. But so there's been a lot of work on making this just m plus n. Okay, so I mean it's a natural question, but I don't know why one would spend their life thinking about this, right? But people do. Okay, but there's actually a very simple randomized algorithm which can do this. Okay, and it's not known if there exists a deterministic one. So the best known algorithm has m plus n times a really slowly growing function of n, which is called the Ackermann inverse. Okay, so this is like this extremely slow growing function of n, but it's not quite constant. Okay, so that's it's constant for all practical purposes. Okay, so there are even faster than this algorithms that I know. Okay, and this is one of those things that a lot of people think about. Okay, so this is what I wanted to say about spanning trees. Any questions about spanning trees? So it's a basic graph problem, so all of you should, I guess, at least know what a spanning tree is and some simple algorithms for it. Okay, so it's one of the few graph problems for which a natural greedy algorithm works. And one other thing about this, about the Prim's algorithm is that note the resemblance to Dijkstra, right? So you have some set, then you're always picking the smallest weight edge out of it. Okay, so it's kind of like Dijkstra in that you're growing a thing. But there you look at the total distance from the source, not quite the minimum edge way down. Okay, so I just thought this is, it's a very similar algorithm. Okay, so in fact, Dijkstra's original paper has both an algorithm for shortest path and an algorithm for spanning tree. So I put up a link to that. So for those of you who are interested in the historical development, that's nice to look at. So this was at a time when people didn't know of polytime algorithms and so on. There was no notion of polytime algorithms. Okay. Okay, so let's now talk about a slightly different topic. So this is actually a very powerful notion. Okay, so it's used in a lot of applications, and this is the notion of flows in a network. So it's probably the only very non-trivial algorithm we will see in this class. Okay, so it's something that you would not naturally come up with. Okay, so all the algorithms we've seen so far, if you think about it for 10 minutes, you could probably have come up with them, right? But this is tricky. Okay, so what's the problem here? So we have a directed graph. So let's think about some directed graph with some edge weights. And there are some edge weights. And the goal of this problem is, so you have two special vertices. So they are called source and sink. Okay, so I'll call them S and T. So source will always be S and the sink will always be T. Okay. And so the goal is to, so if you think of each of these edges as being some kind of pipes with a certain capacity. Okay, or you could think of electrical networks or something like this. So the goal is to send as many units of water from S to T as possible. Okay, so if you in this pipe analogy, so think of this as being a pipe of, let's say, radius 1, radius of capacity, whatever, 1. Okay, so this the weights are called the capacities. So the common application for this are networks. Okay, so when so in the early days of the internet, so this is how you would model. Okay, so this is the channel capacity or something like this. This is the amount of data you could transfer per second, something like this. So this is the capacity, and the goal is to find a bunch of paths, okay, that go from S to T, so that you transfer the maximum amount of information. Okay, so this is, if you think of this as capacity, so then maybe this is 3, this is So in this graph, if I picked this edges, now I could, so this is what I call a flow. Okay, so a flow has a subset of edges, and for each edge there is an. So here I could be passing some flow 1, and here there is. I could try to say, okay, here I'll send 4, but and then I could have 4 going out here also, but then the capacity of this final edge is only 3. Okay, so I can't send that. So I'll have to have only a flow of 3 along this path. So is this intuitive definition of flow clear? I'm just trying to first give you a sense of it, and then I'll write down the mathematical formulation. Okay, so you want to find as many paths as you can between S and T. Okay, and so that no edge has more flow on it than its capacity. Okay, so a non-trivial thing could be, for instance, you could have a vertex. You could have, let's say, capacity of 4 here, and maybe here there's a capacity of 3, but then maybe there's a capacity 1 edge out here, a capacity 2 edge out here, and then you go from S to T, and now you can actually send 4 units of flow from S to T, because you send out 4 there, and then you split the flow. So then 3 will go from there, from the top edge, 1 will go from here, and this one will end up going over here, and so on. Okay. So I'll come to the formal definition in a bit, but is the intuitive notion clear? So think of it as just some pipes with capacities, and you want to send as much units of water as possible. Okay, so yeah. And you wanted to find how much throughput you can have. Okay, and this is also a common problem in networks, for example. Okay, so flows have a lot of applications. Yeah, as I said, it's one of these slightly tricky problems, so it's difficult to come up with this kind of analysis. Okay, so let me start by defining the max flow problem. So maybe first I will go to the formal definition of flow. So given a directed graph and with capacities, and a source and a sink. Okay. So a flow is formally just defined as a function that maps edges to real numbers. So what this means is, for every edge, there is a value of the flow on that edge. Okay. So for every edge E, there is some value Fe. Flow is a function F maps E to R such that A. So the first condition you want is that for every edge, for all edges E, Fe must be smaller than or equal to the capacity of that edge. Right? So in this, I'll write C of E to be the capacity of this edge. So this basically says that no edge exceeds capacity. So this is a natural constraint. And second, so these are the more interesting ones. So these are what are called flow conservation. So what this means is, for any vertex other than the source and the sink, for any vertex other than S and T, flow into this vertex, so let's call this vertex V. Okay, flow into V is equal to flow out of V. So this is a slightly trickier constraint, but it's a very natural one, right? So it's what we are saying is there's no accumulation of flow anywhere apart from the source and the sink. At the sink you have to accumulate, and maybe there's flow going out. Okay, so in every other node, the net flow is actually zero. Okay, so that's again the intuitive definition of flow, right? So if something comes in, it's got to go out. So this is the definition of an ST flow. So you have S and you have T, and on every vertex, on every edge, you just have some F. And of course, F has to be non-negative. So you could have edges in both directions, in which case you could have non-negative weight on both of them, but that's fine. So just think of, so for these purposes, you can just think of, if you have two edges like this, just think of them as two different paths, right? And they have nothing to do with each other. Any questions about this definition? So it's the formal one. Good. So let's now define this max flow problem. So the maximum flow problem is this, again we defined earlier, is given S and T, find the flow with max value of sum over E going out of S FE. So this is the value of the flow, right, intuitively. This is how much flow that's actually going out of S. So we said that you can only have flow going out of S and then going into T, right? So you want to maximize it. So this is the maximum ST flow problem. And we want to come up with algorithms for this problem. So, and we'll also see how this is related to things we've seen before. So let's go on. So the most natural algorithm you will come up with when you try to do flows is okay, so I want to route, I want to send as many units of flow as possible from S to T, right? So you can say, okay, as long as I see a path from S to T, route some flow along that path. Okay, so let's see what this means. So I have S, I have T, and I have a bunch of edges, let's say. And maybe there is this edge has weight 2, this edge has weight 2, this edge has weight 1, this edge has weight 2. So something, right? So I have a bunch of weights. And so the algorithm I want to use is a greedy one. Okay, so I look from, I first look from, try to go from S to T. And I try to see if there's a directed path, okay, such that all the capacities along that path are strictly bigger than 0. Okay. So this is natural because in this what you would do, right? So I find this path, let's say. All capacities are bigger than 0. And along this path right now, I can send 2 units of flow, right? Because all capacities are actually bigger than or equal to 2. Okay. So I can send 2 units of flow. So let's say I do that. So then the capacity, the remaining capacity of this is 0. So I send 2 units like this. Okay. So maybe I should write F equals 2. And here I have F equals 2. So the remaining capacity is 1. And I have F equals 2. Remaining capacity is 0. So at this point, okay, so I made this choice. Now, can I send more flow?
Yes.
Yeah, so you have a bottom path, right? So you can say, okay, so I have this new path now. And so I can send 1 unit of flow. I can't send more than 1 unit of flow because, I mean, this is the rate determining edge, right? So this edge has only capacity 1. So I can't send more units along this path. So, okay, so then maybe I will send 1. Okay, so I'll send F equal 1 here, and this has capacity 1 now, remaining capacity. Now this has capacity 0, it has capacity 2 left. Okay. So, everyone clear with this notation? I'm just writing the remaining capacity. Maybe I should have used a different color that would have made things clear. Okay. Okay. So now is there any other path left of some remaining capacity?
Yeah.
So you could do something like this, right? So you could go
Diagonals.
Oh no. So here the capacity is 0. Okay. So here the capacity is 0. There's no path that could go out like that. So any other path should have come like this, right? So let's say I start off here. Okay. Then I could try going there. Okay. But then there's no path from this vertex U to T, right? So there the capacity was 0 again. Okay. So it turns out in this example there is no other path you can come up with. Okay? So, sorry?
So there are diagonals, right? So if we
Which ones?
from the second node down to the third node.
Right, but your flow has to start from S and go to T.
Yeah, so you can go this way, right? So from S there is a ray.
So let me label all the vertices. Okay, so let's call this is U, this is V, this is W, this is X. Okay, so what's the path you are thinking of?
VXT.
From S to V,
Yeah.
but S to V is 0, right? There's no capacity from S to V.
Yeah,
If you start over and do it that way.
Oh, you're saying this is not an optimal solution?
Right.
It depends on how you start.
Yeah.
Yeah, so this is the usual, I just want to say that you have the usual greedy problem. Okay, so that you started out by picking this path, but that was wrong, right? And but you can't afford to like try all paths all the time, right? So this is the usual problem with greedy. So it turns out, so all I want to say is, at this point you can't add any more flow. Okay, so you got stuck. Cannot add more flow. But on the other hand, so what's the, but before we go there, what's the total flow you've sent so far? 3, right? So you sent 2 first along this path and 1 along this path. And this is the maximum. But for this instance, turns out you can do something slightly better. So you could have first sent flow like this of value 2 and then sent a flow of 2 along this vertex, along this path. And this would have been nicer. Okay, so this would actually have a flow value of 4. Now, actually, is this the maximum? Can you do 5?
No.
Why not?
No, because the direction from S is only 4. The output of S is only 4.
Yeah, so there were 2 edges out of S. One of them had capacity 2, both of them had capacity 2, right? So there's no way you could have sent more than 4 units of flow out of S to start. Okay, so that's in this case a very easy way to show that this is actually optimal. But so this is the main problem with greedy, that it need not find the optimum. Oh, and then you may have to restart, and then it's not clear, right? Okay. So, and if you had a big graph, these sort of things, it's not clear how you do, right? So everyone see the problem with greedy, that you can get stuck. Okay, so this is a common problem with greedy.
It's more expensive actually, because you have to always to go from S all the way to and then come back. It's very expensive to do.
Say that again.
In the implementation all the way, it's also expensive.
Yes, even this is expensive.
Yeah.
Yes. Yeah.
That's one.
But it turns out for flows, all the neural algorithms are relatively expensive. Okay, so they're not as cheap as M plus N or something. So that's again one of the big problems. And here there's actually a big gap between what we know you can do and what you know you can't. So, okay, so this is a greedy algorithm. So the key idea behind this Ford-Fulkerson algorithm, so this is, we're going to see this algorithm called Ford-Fulkerson algorithm. So this is from the paper that I just put up. Ford-Fulkerson. I think I might be mispronouncing his last, the second name. Yeah, never mind. Okay, so the main idea behind this thing is so they had a very clever way of trying to, in some sense, correct for mistakes that you might have made. Okay, so let's go back to this example. Okay, so I'm going to draw a simpler example where the weights are only 0, 1. Okay, so because numbers get confusing, right? So let's draw a simpler example where you will also get stuck. Okay, so the simpler example is you have the same vertices. Oh. So here you have S, and we're going to draw an example where all the weights are just 0, 1. Okay, so it's the same graph, just changing the weights so that I don't know why I started with so suppose all these weights are 1. Now there is no edge here. Okay, so that's like saying this is 0 edge or whatever. So in this case, if your first path was that, there's no way you can improve, right? Because you've used up all the. So you can't go like this. Okay, so in some sense you've made a mistake with going like this. But then if you had started with this guy, then that would have been an extra path. Okay, so but in this example. So suppose you started with this path. Okay. Now, the good thing that these guys observed is that, so earlier what we were doing was we were going back and then we were changing these capacities, the leftover capacities of these edges. Right, so we're just going back and then replacing this by capacity 0, replacing this edge by capacity 0, this edge by capacity 0. But instead, what they said was, suppose you just add a back edge, okay, of capacity 1. Okay, so in this case, this is the path you found. So add back edges of capacity 1. So let me see if so does this, yeah, okay, so from next time I will do this. Okay, so basically you add back edges of capacity 1. And the idea is, if you now find a path that uses a back edge, then you can think of it as, in some sense, removing the forward edge that you've used before. So that's like the very ingenious idea that these guys came up with. Okay, so they said, come up with this, so you still go ahead and replace the capacities like you did before. But now you add these back edges that have capacity equals to whatever flow you send. Okay, so for this example, is this procedure clear? Okay, so we'll come up with a formal thing later. But in this example, this is what they do. And now, in this graph, where you have these back edges, so can you actually find can you now route more flow from S to T? Can you now take some ST path? Which one? I'll have to label them, I guess. So this path, right? So you go from S to U, U to V, this to W, and so you have this somewhat complicated, but you have a path. Okay. So now, what you can think of doing is, so initially you had this flow, and now you have, so there's only a few colors I can use. So now you have this flow. And you can think of adding up these flows. And when you add up, this negative edge kind of cancels the first forward edge. Okay? So, I mean, remember there was one forward path going like this, and then there was this negative path going like this, right? So the sharing between these paths is this edge. Okay, so it's the V to W edge. Right? So the first path used S to W, W to V, and so on. The next path was using this thing. Was going from V to W using this back edge that you placed. Okay. So now you could say, okay, so if you add up these two flows, so to say, okay, so then what you get is essentially the flow where you have this part doesn't get cancelled. Okay, so the S to this, and then you have this. So this gets cancelled, right? So because you chose this edge and then you chose the reverse edge in a different path. So this edge gets cancelled, and now you have this edge that remains, and this is from the blue thing, and you have this edge which is 1, and again you have this, because this part of the blue path, and then you have this which is also part of the blue path, and you have an edge of weight 1. Okay, so is it clear what happened when I cancelled out these two flows? Yeah.
For the blue part, you were also selecting greedily.
Yes. So that's the point. So what at every step, I mean, so first I select greedily.
Yeah.
And then I put these correct, I mean, so think of these as some kind of insurance edges. Okay, so it's like in some sense you allow the possibility of correcting some mistake you may have made. Okay, so I mean, if this were actually part of the optimal solution, then you probably won't go back and correct it. Okay, so but you just put these edges to say that, oh, okay, so if I ever want to go back and correct some of the flow I put, then I will use those edges. Okay, so that's the role these guys are playing. Okay, and now in this new graph, if you found a path, then you'll go ahead and find that path, and then you will add these two flows. And adding is the tricky part. So we're going to make sure that, I mean, actually this is a very simple example in which only one edge gets deleted. But you could have things where you send some flow, part of the flow gets cancelled out. Okay, so you can imagine settings where part of the flow gets cancelled out and part of it remains. Okay. But all you have to verify is that this is still a valid flow. Okay. So that's what we'll see now. So is this idea clear? So the main thing for you guys to notice is this notion of adding back edges. Okay? And this is as a potential way to correct for mistakes that you make. Okay, so this is the main novelty in this algorithm. And turns out you can use this now to essentially come up with a good flow.
But you could keep increasing the weight on the back edges to get different flows. Could you do that? So you're adding packages.
Yes.
And the flow possible per package here is 1.
Yes.
But I could have cases where I try for 1, 2, 3, 4, and I could potentially get
more and more accumulating black edges. Yeah, which makes sense, right? Because then you're saying that you had one path and then you found another path which used the same edge in the forward direction. And that's why you added more to the back edge. And that's fine, because next you might realize that I don't want both these edges. I actually want some other edge. That's why you can cancel both of them. Okay. So that's the general thing. Okay. Main idea is this notion of adding back edges. So I'll formally say what that is now. Yeah.
Can you go back to the diagram?
Yeah.
So initially you came from S, W, V and T.
Mm-hmm.
Then after that, when you tried out the SU edge, you realized that you were having a roadblock.
Yeah.
So when you backtrack from T to V and V to W, why didn't you delete the VT edge and just the WV edge?
Oh, so why did I just delete that?
Yeah, because you came.
Because that edge was not cancelled out, right? So the new path, the blue path, it uses this new edge, uses that new edge, then it uses this back edge, and then it has another new edge and it has another new edge. Okay? It's not cancelling out this forward edge, right? So the green. So what we are doing is we are only cancelling out things where you had a green forward edge and a blue back edge. Okay, so that's the only thing that is cancelled out. So think of it algebraically. So think of it as, I mean, just flows that have signs, right? And then on every edge, you kind of add up the positive and the negative guys. And along this path, the initial green flow had a positive weight, blue flow had no weight. Okay, so it never got cancelled out. Okay. So that's how the proof will go also. Okay, so that's how the formal reasoning will also go. So you will just treat these flows as numeric values, and then you add up the flow on every edge. So that's what is going on. But yeah, but I want you to, this is actually a very subtle point, so I do want you to go back and think about this, because this is a very nice way of ensuring you can correct mistakes you've made so far. And this is rarely possible for greedy algorithms. Okay, so there's only a few cases where you can do this. Alright, so let's formalize this. Okay, so the way these guys formalize it is, so you want to have a general framework, right? So what you want to do is not just you have one path and then you add negative edges along that path, but what we want is a general framework. Okay, so what we are going to come up with is the notion of, suppose you have a flow so far. Suppose you have current flow. Okay, current in the present sense. Okay, current flow. Then you come up with what is called a residual graph. So define what is called a residual graph. And somehow flows inside this residual graph will help you find bigger flows in the original graph. Okay, so that's the flows in the residual graph. Allow you to a larger flow in G. Okay. So this is the main idea behind this Ford-Fulkerson algorithm. Okay, so these are the rough steps. Okay, so what you do is you start off with the zero flow, okay, and zero flow, the residual graph will be the graph itself, and then you will find some path or find a flow, whatever you want, and then you will work with the residual graph for that flow, and then keep doing this. Okay, so this is how this algorithm proceeds. But let's define what this residual graph is. So is the rough idea behind the algorithm clear? So it's essentially you keep making some choices. They could be greedy, they could be whatever, and then you leave open the possibility for correcting them by using this residue. Okay, so let's define this residual graph. So I said that you have a G. We have G, and we have a current flow F. And this graph, we'll call this G sub F. Okay, this is a new directed graph with capacities. Okay, and the way I want to define this graph is it has the same edges as before, okay, but you could potentially have backward edges also. So it has the same edges as before. But it has two kinds of edges now. So it has these forward edges and backward edges. And the forward edges are precisely the following. If the capacity of E, okay, so E was some edge in the original graph, so if its capacity was bigger than the amount of flow that this F, okay, so the current F puts on E, so then you have a forward edge. So then we have forward edge of capacity C of E minus F. So this is basically saying if you are at capacity, you make it zero. Okay, so that's all it's saying. And then you, essentially it's this edge. And then you have backward edges. So for backward edges, you have them as long as Fe is bigger than 0. Okay? So whenever you have a non-zero flow along that edge, you want to have the option of correcting that flow. So as long as Fe is bigger than 0, you have a backward edge. Of capacity Fe. So this is the slightly tricky thing, since you are now defining this graph, and this backward edge has capacity equal to the amount of flow you put. So is the definition of this residual graph here? So here you have the original graph with capacities, and you have some flow inside it, some feasible flow, which means all FEs are smaller than the corresponding CEs. And now you define this new graph, which is G sub F. And this has smaller capacities for the forward edges, and it has some backward. And so the main claim, the reason you define this is this claim. Okay, so the claim is the following. So this is what we intuitively did in this example. Okay, so what this is saying is, you consider this residual graph. Okay, so this is so you start with G and you start with any flow F. Okay. And now you look at this residual graph, and let F prime be a flow in this residual graph. Okay. So remember, flow is just, for this purpose, think of flow as just some function. So flow F is just a function mapping edges into real numbers, right? So this is what we said. And now you have this new flow F prime, and this is a flow in G sub F, flow in the residual graph. Now what is F plus F prime? So what would you expect this to be? Sorry? Well, no, this is a flow, right? So this is again, should algebraically be roughly the same thing, right? So if, how would you define F plus F prime? So this is, we should try to follow, use the kind of example we did last time, right? So in this example, what did we do? So F was this green path, and the residual graph was this graph that had these back edges. Okay. And in this graph, you found this blue path, and then we were adding things up. And so how would you define F plus F prime?
They cancel each other.
So they cancel only if F prime uses the negative edge. Okay. So if both of them use the same forward edge, then they just add up. Okay. So you can just think of this algebraically as, if you think of F as a function that maps E to R, E to real numbers, then F prime is another function. It's just that some edges could have negative weights, because these were the things that where you use the back edges. So if you use back edge, then treat flow as negative. And so this is F plus F. Okay. F plus F prime. We are saying that F plus F prime is a valid flow in G. Valid flow means, what does valid flow mean? Yeah, the two conditions we said before, right? So all capacity should not be violated, none of the capacity should be violated, and the total, and for every vertex you have conservation. But conservation is trivial, because if you add up two flows, if you add up two things that satisfy conservation property, then the sum will also satisfy conservation property. Right? This is this basic. So for F and F prime, for both you have this fact that sum of the things coming in is equal to the sum of things going out. So if you add those two also on an edge by edge basis, then also you're going to have the same problem. So it's like saying two sets of numbers sum up to 1, sum up to 0, then their sum also sums up to 0, right? So that's basically the reason. So this is why conservation is trivial. I don't know if I introduced the word conservation, but this is what it's called. Flow conservation just means flow coming in is equal to flow going out. And capacities are a bit trickier, but intuitively it should be easy because you had this flow F. This defined these new capacities, right? So for the forward edges, the capacity was only C of E minus Fe. Okay. So the most flow that F prime could have put on this edge is only C of E minus Fe. Okay, because this was a new capacity in this residual graph. Okay, and those two add up to only C of E. Okay, so the total flow on this never goes more than C of E. Okay, so think about this for a second. Total positive flow never exceeds C of E. The reason is that total forward flow, I should say. So, and the reason is the forward edge in this new graph just had capacity C of E minus Fe. So the most F prime could have put on that is this amount. And if C of E was equal to Fe, then the edge would have capacity 0. So this could not have put anything. And backward edges, of course, always cause a decrease in the capacity. So they never cause capacity violation. So any questions about this? So this one, it's one of these things that you should think about for a bit and convince yourself, okay? Because you have to think mainly about what's going on. Be careful about the negative weights and so on, right? Because that's how we're doing. But this abstraction is something that I want you to keep in mind. So what we are doing is, instead of keeping track of what's going on in the algorithm in some complicated way, we are just saying there is a flow at this point. And based on that flow, I am defining this residual graph G sub F. And all I am arguing is, if I have a flow F prime in the residual graph, then F plus F prime is a valid flow in G. And the value of this flow, I should forgot to say that. And the value of F plus G, F plus F prime, is equal to value of F plus value of F prime. This is again easy to verify, but it's good to write this down in this claim. So, and that's just because out of S, there is now F plus F, value of F plus value of F prime coming out. Right? So, yeah. So that's why this has to be this, and conservation is satisfied, so this is a valid. Yeah.
So when you find the residual and combine them, will it always be an improvement, or will it sometimes be the same?
It doesn't have to be an improvement. The way I defined it, it could even be negative if you want. I mean, if you had a negative flow, which means you can think of as just a flow from T to S or something like this. If you add such a flow, then the value could drop. So, but yeah, clearly in our algorithm we'll only add stuff. Okay, so this is what says that you can always improve, right? Okay, I guess I'm out of time. So maybe next time I will show this claim. So this is the other very important claim. So let's understand the claim and then we can break. Okay. So what we are going to do is, what we're going to show is, if you have two flows in G, okay, and suppose F1 has a smaller value than F2. Okay, so F2 is the bigger flow. Then what this claim says is that you look at the residual graph for F2. Okay. So Oh, sorry, I should say F1. Okay, so this is a type of that. So think of F1 as the flow we found. F2 is the optimal flow. Okay, so the value of F2 is potentially larger than the value of our flow. Okay. Now, what you look at the residual graph of our flow. We are saying that there is this new flow you can define called F2 minus F1. I'll come to what that means in a bit. Is actually a valid flow in this residual graph. This will say that as long as our flow is not optimal, you can actually add something else and you can improve this flow. Okay? So this theorem shows the existence of an improvement. Okay? So this shows improvement exists. Okay. And what this implies is that improvement actually exists through a path, and that's how you will end up improving. Okay, so we'll see this next class. Next class also we'll be reviewing stuff. So I guess I'll stop after the proof of this claim, and we'll be reviewing things we've done so far so that you have something going forward to the grade. Okay, so and for those of you who missed the first part of this class, the main announcement is about the final. Okay, so it's the 16th Friday, 10:30. Okay, same.